Curious. Standard physics dictates that the Big Bang should have produced exactly equal amounts of matter and antimatter. Because these two species destroy each other on contact, a perfectly balanced early universe would have annihilated itself in a fraction of a second. This would have left the cosmos filled with pure light, devoid of galaxies, stars, or the chemical building blocks of life. Yet, we inhabit a universe made of physical stuff. A tiny fraction of matter survived the erasure, leaving a massive glitch in our standard models. The mere fact that we exist to observe the universe proves that our current understanding of cosmology is incomplete. This survival problem coincides with two other major anomalies. First, standard model neutrinos have an observable mass of roughly 0.1 electron volts. In the world of particle physics, that is so light it challenges standard theoretical expectations. Then there is dark matter. The greased Chemionkowski bound suggests an upper mass limit of about 300 tera-electron volts, but our observations of galactic rotation suggest a much heavier, unseen presence. These three issues, matter survival, neutrino lightness, and heavy dark matter, converge within a single theoretical framework, the extended BL model. At its center is a proposed superparticle called the right-handed neutrino. If this particle exists, it carries out a triple mandate, providing a unified explanation for all three of these cosmological glitches. This diagram shows the scale of the first mandate. The observable neutrino sits at a tiny 0.1 electron volts, while the right-handed neutrino exists at a staggering 10 to the 14th power giga-electron volts. This is the type 1 SISSA mechanism. Their masses are inversely proportional. As the heavy right-handed particle is pushed incredibly high, the standard neutrino's mass is forced correspondingly low. This means the neutrinos passing through your body right now are only light because right-handed neutrinos are so incredibly heavy. In the hot early universe, the first generations of these heavy neutrinos were unstable. They rapidly decayed into standard model leptons and Higgs bosons. These decays violated charge parity symmetry. Because of this violation, the superheavy neutrinos decayed into leptons, the building blocks of matter, at a slightly different rate than they decayed into antileptons. This process, called leptogenesis, created a tiny lepton excess. Fast-acting standard model processes, known as phalerons, then converted that excess into baryons, the protons and neutrons that make up the visible universe. When the bulk of matter and antimatter eventually annihilated, this slight excess survived. This microscopic decay imbalance is why the visible, massive universe exists today. While the first two generations decayed, the third generation right-handed neutrino was protected by a property called Z2 symmetry. This made it a permanent survivor and a primary candidate for superheavy dark matter. Without decaying, the dark matter survivor's concentration remains dangerously high. To solve this, the model uses a zombie collision. The survivor collides with a lighter sterile neutrino, the zombie, converting the survivor into more zombies, dropping the dark matter population exponentially. Finally, when these lighter zombies decay, they inject massive radiation and entropy into the universe. This dilutes the concentration ratio, perfectly matching the dark matter density observed today. This two-step destruction process allows dark matter to reach masses of up to 10 to the 13th power giga-electron volts, well beyond the 300 tera-electron volt limit, while still producing the correct relic abundance. Traditional particle colliders are too weak to ever detect a 10 to the 13th giga-electron volt particle. Proving this theory requires a different kind of observation. The same symmetry-breaking event that forged these heavy neutrinos also created one-dimensional topological defects known as cosmic strings. These strings continuously collide and snap, producing smaller loops that emit a constant stochastic background of gravitational waves. Observatories like the LIGO detector shown here are currently searching the sky for this specific wave spectrum. Gravitational wave astronomy allows us to monitor these ancient ripples in spacetime, effectively capturing the signature of dark matter's creation. To keep exploring the frontiers of physics, remember to like, subscribe, and suggest our next topic in the comments. Thank you to our sponsor, Synestic Systems LLC, founded by Shane Persinger, for supporting our look into the early cosmos.